Hello everyone, I'm Yatin, and in today's lecture we will start with physics of LLMs, right? So far in the course, we have looked at what are language models, right? We looked at the architecture of transformers, which has become the most common language model these days. Then we looked at how to pre-train the language models, how to post-train them, and then we looked at various alignment techniques as well, where we covered RLHF, DPO, PPO, right? All of these were training techniques. We also looked at how to efficiently scale the training, because pre-training is really massive. Without scaling, we really cannot do anything, right? So we looked at how to efficiently scale the pre-training. Then in the applications, we also looked at how to use LLMs in real world scenarios. For example, if you want LLMs to answer questions from a specific document or specific domain, then RAG is the go-to technique. But then RAG alone may not suffice. So we looked at various agentic patterns, which also included tool calling and all of those. So these were essentially applications of LLMs to serve the real world problems. Okay. And then we'll also looked at how to mimic and induce reasoning within these language models, right? So till now, our focus has been mainly on what are language models, how LLMs work as a black box, how can we adapt them for real world scenarios, how to use them, right? We haven't yet focused on, why behind the how, right? We know how they work, but do we know why they work? Is there any theory behind the workings of modern age transformer language models? And that is the focus of this lecture and maybe the next lecture as well, right? But before we begin, when we look at the word theory, what does it mean? What do you guys understand with this word? When we say we want to look at the theory of language models, what pops up in your mind? Anyone? Fundamentals of what? So again, what do you mean by first principles there? What do you mean by basics? Axioms, right? So essentially what you are trying to reach, where you're trying to reach essentially is mathematics of transformers, right? Can we have some computational learning theories or statistical learning theories? We understand, for example, linear regression very well. We have a lot of theories behind it, right? We also understand shallow networks, right? We have learning bounds for those, right? So this essentially means, the maths behind the science, right? So again, in the learnability theory, we see dimensions, pack learnability, formalism, generalization, error bounds, right? So this is one extreme. But then in some other world, theory also means ethology, which is, science of animal behavior, which essentially means that you take a monkey, put it in an environment and observe how it behaves, right? And try to formalize from their behavior, right? And this is what people have been doing right now. They're treating these LLMs as monkeys, playing with it to come up with general theories, right? Well, now both have their pros and cons. For example, if you look at the maths side of things, when you look at statistical learning theories, the biggest pro is its formalism, right? It's very rigorous. We get theorems which will hold. But then the difficulty there is that it's too hard to understand even for experts, right? I also don't understand most of the learning theory behind machine learning, right? So it's very difficult to understand, and it's very slow. It takes a lot of time to develop those over years, right? And the assumptions are also very idealistic. When you have to make a lot of idealistic assumptions when you are dealing with, for example, you need to assume the data distribution, but the real data may not follow that distribution, right? So there are a lot of assumptions, idealistic assumptions that you have to make, which makes it difficult to understand real world application, a real world thing like today's large language models. Whereas if you look at ethology, its biggest pro is that everyone can do theory. Anyone can take the APIs and play with the language model and try to come up with some conclusions, right? And this has been useful as well. For example, the phenomena of chain of thought or tree of thought, right? All of these came from this kind of science, where people were playing with the language models, right? And then, of course, here the major issue is that it's too subjective, it's less rigorous, and it may lead to false claims, right? Whatever we observe for two language models may not hold in general, right? We may not be able to derive generic phenomena or generic laws which applies to all language models or all transformer based language models, right? So let's first in detail look at what are the issues with ethology as a science if we try to apply it to language models. So the first major issue is that we are studying a very specific model, and the learnings may not generalize to other LLMs, right? So if I look at the history of science, it resembles geocentrism, where people looked at two models, sun and the moon, and came up with the conclusion that Earth is at the center of the universe, right? So that's the issue. If you observe only few models and try to draw conclusions, you may draw false conclusions, and that is the biggest issue here, that we are studying very specific models. That is one. The other issue is that there is no control over the training data. For example, if I have a model which gives me 90% performance on mathematical reasoning task, let's say GSM 8K, right? So GSM 8K is a data set which contains mathematical reasoning problems, 8,000 mathematical reasoning problems. Now, is it because it genuinely has those reasoning capabilities, or is it because there was some data leak somewhere, right? That the model has seen those problems during their training, right? Model creators may not do it intentionally, but it can happen unintentionally as well, right? Because they're crawling the web, and someone might have released similar problems or translated those problems and put them on the web, right? So that is the other issue, that the conclusions that we draw based on some benchmarks may not hold, because we do not know. There is no control over the training setup and the testing setup. We don't know whether they are non-overlapping or not, right? Then so there was this paper, a sarcastic one, which said that pre-training on test set is all you need to get good performance, right? So if you train on the test, then of course your performance is going to be 100%. All right. The third issue is that when we play with APIs or the language models like that, if we treat them as black box, we do not come to know what is happening inside, right? We do not. It doesn't reveal the inner mechanisms. Then another big challenge is the attribution. For example, let's take this example. Was Joe Biden born earlier than Nancy? Now, what do you think? Will ChatGPT or Llama be able to answer this question or not? Yes, I also thought so. But then I was also surprised that its answer was incorrect, even though it has the correct information. It knows that Joe Biden was born on November 20th, 1942, and Nancy was born on March 20th, 1940. Even then it says yes, right? And yeah, and same holds for Meta as well. It also says yes. So I was surprised when I looked at this example, right? I took it from a tutorial, that I actually had to go and test it myself. So I asked ChatGPT, was Ganguly born before Sachin? It says no. Sachin was born before Ganguly, right? And look at the birth years of Sachin and Ganguly. It's incorrect. So it's really, it was striking for me as well when I looked at it for the first time after reading this paper, right? And you can go on and on. For example, was Sachin born in an even year? yes, Sachin was born in an even year in 1973, and then after it has spit out the year, it goes on to correct itself. No, he was not born in an even year, right? And then it is, unabashedly claiming that I'm GPT-5, right? So these examples from the paper, they are with GPT-4, and even GPT-5, right, fails. This is the most latest version of Chat GPT. So if we try to analyze this question, and if we have to understand whether, why is model failing here, we need to attribute its failure, right? It could be because the model cannot extract the birth year of Sachin. So if you look at the question carefully, it needs two things. It needs to first extract the birth year and then needs to reason over it, right? So first failure point could be that the model cannot extract the birth year. It doesn't have the knowledge. So this is the knowledge part of the model. Or it doesn't know what even means, right? So this is also part of the knowledge, or concepts, right? This is knowledge, this is concepts, or you can mix them together, right? Or is it that model can extract the birth year, knows what is even, but still cannot answer, right? So if we have to categorize this failure case into one of these three buckets, we cannot do if we are working with black box LLMs, because their training is not controlled, right? If we can ensure that this and this holds, only then we can claim about E, right? So this is one of the challenges, in ethology, applying ethology to understand language models, which is that success and failure attribution is very difficult. Is it failing due to lack of knowledge or lack of ability to extract the knowledge? These are also two different things. It may know, but it is not able to extract that knowledge, right? Or is it due to the lack of ability to reason over that knowledge, right? And if it is succeeding, that is also difficult, because even in the case of success, attribution is difficult because let's say, after I have asked this question, they will use this as a training data. In the next month, it may get updated. So it might have seen that compound fact as it is without understanding it. It might just memorize it, right, without doing any reasoning. So we need to control for that as well, right? So this is very crucial, that we attribution of whatever we observe is very difficult if we are playing with black box language models. So what is the alternative to this? What should we do, right? And that's what the series of paper, Physics of Language Models, propose. It's a series of work by Alan Zhu. He's in Meta, and they define four fundamental principles, founding principles of their study. The first is that they decompose intelligence into multiple building blocks. So they want to understand. So if you have to do this, for example, error attribution, we need to understand whether it is knowledge or reasoning which is missing, right? So if we take one complex language model, it's difficult to bifurcate these two. So what they are proposing essentially is that we should take each of these components and try to understand them separately, and have control experiments for that. So that is the second proposal, which is that we should do controlled study, which essentially means that so for example, to understand reasoning, we should first control for the fact that the model knows. We should ensure that the model knows the information, knows the birth year. Only then we should check whether it can infer whether it is even or odd, right? So that is the second fundamental principle, and this also avoids data leaks. We can ensure that there is no leak of the test data during training, right? Then the third principle is that our experiments should be highly repeatable. Right? If there are several knobs that we want to turn on and off, we should be able to do that, right? But if we take the language models which are popular these days, they are really huge and their training cost is really high. So therefore, they advocate experimenting with smaller models, 100 million or 300 million, not 800 million maximum size models. And so that it's easy to repeat those experiments multiple times and change the knobs and then repeat the experiments again. Right? Now one may argue that if we reduce the size of the language models, the laws that we derive, will they be universal? Because a lot of capabilities, they are uncovered with scale. Right? Smaller models may not have the capacity, and that's where the first two things help. That because we are studying each individual intelligence block, we don't want to study the overall intelligence in one go. We are looking at one specific block, let's say knowledge or reasoning, right? And then we are studying in a controlled environment, right? We know the training data that we have. Therefore, because we are working in a controlled environment and we are looking at very specific aspects of intelligence, smaller models are more than sufficient to mimic those aspects, right? Okay. Then the fourth principle essentially is probing techniques. So we recall that when we are treating these language models as black boxes, we do not know what is going on inside them, right? So can we maybe look at the embeddings in the inner layers of the transformer and try to see what information it contains? Right? So they advocate for probing techniques. And now we have been talking about etiology and maths. So if I try to develop an analogy with the history of science, so the coming up with computational or statistical learning theories is similar to writing Principia Mathematica, where Newton derived the entire maths to understand what's going on in the real world, to understand the physics, right? So it's difficult and it takes time as well, right? So his objective was also to understand what's the gravitational laws and the laws of the physics, but for that he had to develop entire mathematical theory or the entire calculus, right? The other extreme is etiology, which is the science of animal behavior, and we saw that this is similar to geocentrism, right, where we observe two models and try to draw universal physics laws. Whereas what these guys are advocating, it's similar to Kepler's laws, right, which were based on the data observed by his supervisor Tycho. So Tycho made a lot of astronomical observations for 20 years. Kepler's laws were based on those, and then Newton's laws were also based on the Kepler's laws, right? So what they're trying to do right now is derive something which is akin to Kepler's laws in language models or for language models. Right. So so with this background, let's delve into what these guys are proposing. They divide the study into three parts. Part 3 is understanding the knowledge, basically trying to answer the question whether models contain the knowledge to answer any specific question or not. Then in part 2 they look at reasoning, and then in part 1 they look at language structures, right? So so they have a very good project page for this, where they have put all of their material, and there is a YouTube channel by the author, and all of these slides are actually taken from his videos, right? Okay, so let's get started with part 3.1, and let's go back to our counter example. The question, which is, was Sachin born in an even year, right? Now if this question is being answered incorrectly, is it because the model cannot extract the birth year of Sachin, or that the model doesn't know what even means, or is it something else? In this part we will focus on this aspect. Under what conditions can model extract the knowledge, and under what condition it fails, right? And we can further divide it into three questions or three probable reasons. The first one is that if model did not see that data during training, it will definitely not be able to extract that. So is this the reason that model did not see the biography of Sachin during training? Second aspect is that if it sees a biography, it's going to be in the form of sentences, whereas we are posing a question. So we need to fine tune the model to extract that knowledge from its parameters, right? So extraction is different from memorization, right? So is the reason that model was not fine-tuned enough to extract the birth years, or is it that model knows these two things? Model knows Sachin's model has seen Sachin's biography, but it is not able to extract the birth dates of all the celebrities, right? It's able to extract, it knows the concept of birth date, it knows the concept of biographies, but it is not able to extract that knowledge for some specific individuals, Sachin in this case, right? So this is what we will study, and to do that, they have a controlled setup. They're training 100 million or 300 million GPT-2 models, right? And they start from scratch, random initialization of model weights, and they create synthetic data so as to, the data that they are using for training has to be controlled, and to do so they create roughly 1 lakh biographies, right? And a biography would contain 6 different attributes for an individual. So everything is synthetic here, nothing is real. There's no one called Anya, right, in the real world, who was born on October 2nd, right? So there are 6 attributes here: the birth date, birthplace, and where the person studied, and what did the person study, where the person works, and what are the headquarters of that place. So these first 5 are independent of each other. This location of the workplace is tied. So if it is Meta, it has to be Menlo Park, California. Right? These two are tied, right? So and for now, let's assume that for all the biographies, the data that they are using for training, it appears in this, they follow the same order. First sentence will talk about the birth date, second sentence will talk about the birthplace, third will talk about the place where the person studied, fourth about the subject, and then fifth about the workplace. But then there are, and they have some 50 templates from where they are choosing each of the sentences, right? Okay, so this is bio S data, which is S stands for synthetic here, and they also create another data set which is a realistic version of this. They take this paragraph and pass it to Llama, right, and ask it to paraphrase it essentially. So this is more realistic paraphrasing of the same information, right? So they have these two different data sets, bio S and bio R. R stands for realistic. All right. Now let's first define the task of knowledge extraction, right? And let's first see what are they using to train the model. What is the training data? So training data consists of these biographies. These are 100K biographies, right? Out of these 100K biographies, they split this into 50K group. This is train and this is test. Recall that in addition to memorization, it has to learn the art of extracting that knowledge as well. So to induce that, they create synthetic QAs, standard QAs on these 50K individuals. So for each sentence or each bit of information, we have 1 question. So for each biography, we will have 6 questions. Right? So what is the birth date of Anya? Right? And then what is the birth city of Anya? What major did Anya study? And so on and so forth. The idea of this is to induce the skill of knowledge extraction, right? And what we want to test are 2 things: whether the model has memorized the knowledge and whether it is able to extract it or not, right? So if I ask a question from the train set and the model is able to answer that, would we say that it has learned the art of extracting the knowledge? We can't say, right? So if it is able to answer the questions from the train set, then it's essentially memorization. We know that it has memorized. Only if it is able to answer questions from the test set, right, which consists of called completely different 50,000 biographies. Only then we can say that model has learned the skill of extracting the knowledge, right? Okay. So the training setup in the first experiment is that they mix these two train data. So this is for in the this is the, you can call it pre-train data, and this is QA data, right? And they mix the two data sets together and learn via next token prediction, right? So understand that they have QA data which is in the form of question 1 and answer 1, right? When we typically train using QA data or instruction tuning data, we try to maximize probability of A1 given Q1, right? But they are mixing it all together in the pre-training stage, where they are creating a sentence with Q1 comma A1, and this becomes my new sentence in the data set, right? And they are trying to maximize the probability of the sentence X with respect to theta. That's what the pre-training objective is. I hope everyone knows that by now, right? Right. So this is the training setup, and then testing setup is the remaining 50k QAs. And what they observe is that it works. If you do mixed training, right? If you have question answers in the training data set, you are able to get more than 85% performance, which is good. We can say that it has learned the art of extracting the knowledge as well, right? But there is a catch here, and the catch is that the ratio of QAR which works. So this QAR represents the fraction of QA data versus the fraction of biographies in the training set, right? So the fraction which works is 80% of QA and 20% of biography data, right? And if we change that fraction for 80%, it works, but if we reduce it, performance drops significantly, right? And what is the realistic scenario? I mean, when you are pre-training a language model using the corpus, using the web crawl, let's say, what would be the ratio of free-flowing text versus question answers which may appear in the text, right? Very less. It won't be 80%. So it won't be a realistic scenario. So it works, but if you have a realistic scenario where it is, let's say, 10%, then the performance is really low for both the data sets, right? So they try to understand what's going on behind the scenes, right? So they take the model which works, let's say they fix it to 80%, right? And to understand what the training, how the training is proceeding, they define 4 different kinds of accuracies, right? One accuracy is whether you are able to predict when this is my data, right? Am I able to predict this token based on the previous sentence, right? So this is, and again I can do this for in domain and out of domain, right? So I have in domain and I have out of domain, right? I can compute the bio accuracy, which is essentially the next token prediction accuracy, right? And of course I want to, the information bits are these 6 bits only, right? Everything else is this it is not invariant. If I have 2 biographies of Anya, the invariant would be these 6 attributes, right? So we are interested in only these 6 attributes, and we compute whether when I'm training, as I train, if I plot a graph, this is the epoch or training step, let's say, right? And I perform accuracy. I want to see, whether model is able to predict this Princeton NJ based on the entire prefix of the biography or not, that we are calling bio prediction, bio accuracy, and we can do this for in-domain biographies and out-of-domain biographies. Right? Out-of-domain biographies are those biographies for which we do not have QAs in the training. Right? This is the difference between these two. Right? The other accuracy is the QA accuracy, the task accuracy. I can check if model is able to answer these questions or not, right, for both training biographies as well as for testing biographies, right? Okay, so this is the 2x2 grid that we get, and we will have these accuracies, four numbers at each epoch, right? So what do you guys think? How would these look like? Let's first look at let's first compare in distribution bio accuracy and QA accuracy. What do you expect? How would it look like? So if okay, let me draw two curves, and you have to tell me which one is for the bio and which one is for the QA, right? So this is epoch and this is accuracy, and it's going to start with 0 and it's going to saturate, and then there is another which also goes like this, which first increases and then red one increases. If I observe these two, which one would be for Q and which one would be for the biography? Right. So what essentially it means is that if I'm looking at this epoch, right, model is able to, has good accuracy on this green curve and low accuracy on the red curve, right? So which of these would be higher? Which one of these is bio and which one of these is QA? I'm talking about let's say in distribution only. Any guesses? Green one is bio and the red one is QA. Very good. That is how we all think. That is how we learn, right? We first read the book and then we go and look at the question answers from there and try to understand those, right? We will first understand, right? That's why, green should be bio. But what they observe is the completely other way around. That because it's a randomly initialized model, right? It is finding it easy to learn from the QAs and then apply it to reduce the perplexity of the biographies, right? So here these two corresponds to BioS and BioR. The blue one, solid blue, is the accuracy on in distribution QA, right? So we have these three things in the training data, right? In distribution QA, biographies out distribution, and biographies in distribution, right? Now it may also be happening because look at the ratios, it's 0.8. It is seeing more of this, therefore it learns more of this. This might also be the reason. But if we look at any other ratio, it doesn't even work. And our objective was to see when it works, why it works, and how it works, right? That's what we're trying to understand here. So the only setup where it worked was where QA ratio was 80%. And there we see that model encodes knowledge using the QA data and not the biographies data. This dotted blue follows after that, right? And then so this is bizarre, that's why they're calling it bizarre, right? And this dotted orange corresponds to out of distribution biodata. So this makes sense, right? This makes sense because this is at least in the training data, right? QA out of distribution is not even in the training data. So of course it's the OOD testing that is happening, and that is the slowest. This red you can think of the solid orange as the QA accuracy, right? So now okay, so this is bizarre and this is not even realistic. We can't have 80% of QAs in our training data. So what is realistic, right? The realistic scenario is what the way models are trained these days. We first pre-train on a large corpus, and once we have pre-trained, then in the second stage we do fine-tuning or instruction following, right? So this is the setup they mimic next, where they first do pre-training and then they do fine-tuning using the in distribution QAs, and then they test on the out of distribution QAs OOD data. And what they observe here is that no matter how you do instruction fine-tuning, right, it doesn't work, it fails, right? So this grid, so what they have done is that pre-training is training the entire training all the weights, and when you are instruction fine-tuning, there are a lot of options that you have. One is that you can do LoRa fine-tuning, right, to ensure that it forgets less of the knowledge that it has, or you can do full fine-tuning as well, right? So this number here, this cell here corresponds to full fine-tuning, where in the instruction fine-tuning phase they are training all the parameters, and this grid here corresponds to LoRa tuning, and on the x-axis they have the rank of the embedding matrix. So recall that in the transformer you have an embedding matrix and then you have KQV matrices, right? So, and on the y-axis we have the rank of the KQV matrices, on the x-axis we have rank of the embedding matrix, right? And the two numbers that you see here, the number in the bracket, this corresponds to the train accuracy, and the number in bold corresponds to the QA accuracy, right? So in full fine-tuning, you see that I mean it's kind of overfitting. Train QA accuracy is close to 100% and test QA accuracy is 7.5%, and in none of these methods, it works. And they also ablate on the model size as well as the data set, so they have the similar result and similar observation on bio S data, bio R data, a smaller model and a bigger model, right? Now, okay, so this is an observation, and now how should we fix it, right? I mean, can you guys think of any way to fix this pipeline? So it's not trivial. I mean, before reading the paper, I also could not figure out. Interestingly, the way to fix this is, when you is essentially data augmentation, which essentially means that in order to actually understand the concepts, you have to see the same information, but in different forms, right? So, for example, even as humans, when we try to understand a concept, we look at it, not in just one form or in just one specific particular way. We encounter it in different ways. I mean, we have the liberty to use multimodal things. We can read and we can see and we can draw the connections between the two. But for the language models, which are, let's say, text-only language models, in order to truly understand the concept, they have to see the same information multiple times. And that happens naturally. For example, in the pre-training corpus, when you have when you have a web crawl or pre-training data which runs into terabytes, it's very likely that the same information is present multiple times there, and that is the key, right? So to again to stick to the principles of physics of LLMs, they do a control study here. They define 3 types of data augmentations. The first one is multiplicity, which essentially means that they take the passage and ask an LLM to paraphrase it, right? And they create M paraphrases. It's the same information, just that the framing is different, right? But the order is same. The first sentence is still talking about the date of birth and so on and so forth. That gives us the second augmentation, which is permutation, meaning that you randomly permute the order of the sentences. And the third and the most powerful and the most unrealistic is that you replace all the pronouns with proper noun, right? So for example, here, instead of using she, you replace this with the name Anya in every sentence. So this is of course this doesn't reflect real world scenario, right? But good for analysis, right? And so these are the 16 variants that they look at. Biosingle is the results that we have seen earlier, right? This biosingle plus permute 5 means that you take the same biography, but you permute the sentences 5, and you have 5 such permutations. This means that you have 5 paraphrases of the biographies, right? And here you permute the sentences along with the paraphrases. So you have 5 different paraphrases, but and the order of sentences is random in each of those, right? And now when we look at the results, we see that it works, right? So this data augmentation gives you 96% performance, right? With full name also you get similar performance. So if you have these two, you don't need full name augmentation. And interestingly, look at this number 4.4. This corresponds to the same data set where now there's random ordering of the sentences in different biographies. Recall that earlier in all the biographies ordering of the sentences was same, and here different biographies are following different ordering. You permute it once, and that version, right, the earlier structure was helping, and this, if you do it just once, it worsens the results from 9.7 to 4.4, right? And these numbers on the right, these are accuracies for the 6 different tasks for extracting date of birth, birth city, universities, major, and so on and so forth, right? So the conclusion here is that if you want to learn the task of knowledge extraction in the fine-tuning phase, you have to augment the data in the pre-training phase, right? So it's very interesting. The skill of ingesting the knowledge extraction, meaning doing QAs, is being imparted in the fine-tuning phase, in the second phase. But for that to happen effectively, you need to do pre-training in a different way, which essentially means that maybe what is happening is that the knowledge is being stored differently, right? If we do augmentation versus no augmentation, what's happening maybe is that the knowledge, the model is learning spurious patterns if you do not augment, right? So what does that mean? And let's see if we can design some tests to look at the inner working of the language models. And that brings us to the next result, which is about probing, right? So how many of you understand what probing means? Hints, okay. So basically we want to probe. We have trained a model. Once we have trained the model, we want to see what maybe the embedding at the last layer represents, right? So that's what probing is, to understand the inner workings of the model, right? And what information it contains, for example, right? So one way of doing that is, you take the pre-trained model, right? And so you take the pre-trained model and pass a sentence through it, let's say, and take the embedding from the last layer, okay, and try to see what information it contains, right? So for example, in this caricature, if I want to understand what the embeddings in layer 3 contains, what I'll do is that I'll take the output from here, pass it through a simple MLP, right, which is very weak to solve the task. It can only, this MLP, the objective of this MLP is just to transform the embedding and extract a particular knowledge. For example, I can train the MLP to find POS tagging, right? Do you guys know what is POS tagging? Parts of speech tagging. Good, thank God, right? So so whether layer 3 encodes parts of speech or not, to test that, to probe it, what we do is that we take the embeddings from here, so basically we pass the input text, we take the embedding from here, we fine tune an MLP layer, right? So this is happening, we are replacing the QA training, the second stage, QA fine tuning. We are replacing it with a probing test, where we are training these parameters phi, MLP parameters phi, and trying to see what is the accuracy for part of speech tagging part, right? So how are they using these probing techniques to analyze the inner workings? What they do is that they feed a biography as an input to the pre-trained model. Recall that this model is pre-trained on 100k biographies, right? And it has saturated, meaning that next token prediction accuracy is 100% now, right? Now they pass the sentence through the transformer model and they look at the last layer embedding of 6 tokens or 6 words which are appearing just before the information carrying bit. So for example, this preposition on, which appears just before the date of birth, this preposition in, which just appears before Princeton, right? So now here and so forth. Now let's look at the specific preposition at, right? If I take the embedding here, for sure, because the training loss is almost 0 and training accuracy is 100%, I will be able to predict meta platforms from here, because that is the task it has been pre-trained on. The embedding here, if I have a probe here, this probe essentially means that I extract the embedding from here and pass it through an MLP and try to classify. So it's a classification task essentially. Classify it into, let's say, predicting the workplace, yeah, look at the company where the person is working, right? Because it has been trained for the next token prediction, for sure this token embedding will be able to predict meta platforms, right? But then, so this accuracy will be 100%. But what about these accuracies? And I take the embedding of this token. Notice that this token already knows that we are talking about Anya. And once I'm talking about Anya, all its attributes are fixed. We know, let's say there is only one Anya in the biographies data, right? The information, to be able to answer these questions, what we want essentially is that the information should be stored on the name of the person, right? Which in this case is Anya, right? So ideally, this embedding should also be able to predict all the attributes, all the 6 attributes, the company name, the company location, and the college name, and so on and so forth, university name, right? But what they observe is that without knowledge augmentation, this accuracy is 0%, right? So these accuracies are so till here, right? Model doesn't know the company name meta platforms, right? It's only after it has seen the remaining 4 attributes that it is able to predict meta platforms. That essentially means that so that essentially means that the model is learning spurious patterns, meaning that so the information about this value 5 here is the company name, is stored not only on the key Anya, but what it has learned is that someone who was born on 2nd October in Princeton, works at MIT, studied at MIT, works at Meta. This is the kind of logic it might have learned. It has definitely learned some logic, because this accuracy is 100%. It has to predict this, right? But the information is not there when we are here, right? Whereas when we do knowledge augmentation, we observe 100% accuracy, right? From all of these positions, which essentially means that as soon as I start processing Anya, right, the embeddings contain the entire information about its biography. And most likely it is happening because in some sentences Anya is followed by birth date, and in some other paraphrase it is followed by where she works, right? So to generalize, and we know that in whatever is the training setup, with augmentation or without augmentation, the training loss is 0, right? With augmentation it is 0. It essentially means, and there are different paraphrases, That means, it is storing the information correctly on the right attribute, otherwise it cannot generalize without augmentation, right? Okay, and so what essentially they're saying is that pre-training with knowledge augmentation, it changes how the knowledge is stored. That's the universal principle, that law that they're trying to come up with. That if you train with augmentation, it is essentially changing the way model is storing the knowledge, right? It is forcing that the model doesn't learn spurious patterns, right? Okay, and that affects whether the whether the model can learn to extract that knowledge in the QA phase, right? So so extraction will depend upon how it is being stored, right? And after looking at this probing, they claim that it is being stored. They hypothesize that it is being stored on the anya, on the key, and therefore even at the first location it is able to answer the other questions. To test that concretely, they design another probe, which is Q probing. Essentially, again, here also what they're doing is that after pre-training, they replace this QA training phase with a probe training phase, right? And what is their probe? Their probe is a linear classifier, weak enough to encode the task, powerful enough to precipitate that specific skill, right? That information. So in this probe, what they do is that they have two special tokens, start and end, and they encode only the name to the model, right? If our hypothesis is true, then this embedding end should be able to predict all the 6 attributes correctly, right? If indeed information is stored in the right key, and that is what they observe, right? That with permutation, the performance in the probing setup is 100% on the right? Now what we are comparing here is that this is the QA accuracy from the previous slides. This is the probe accuracy, Q probing accuracy, and you can look at the pattern as well. Let's not compare the exact numbers, but if you look at the pattern, it's very similar, which essentially means that only if information is stored in the key, it's able to answer, it's able to learn the skill of extracting the knowledge, right? Okay, so this is their result 5, and to sum up, we are saying that knowledge augmentation in the pre-training is necessary to learn the skill of extracting the same knowledge, right? Now the next question is that, is this also realistic, that all the biographies have been paraphrased and the information about all the people and all the information is present multiple times in the pre-training corpus? Is this realistic? Does that happen in the real world data, that all data will be replicated or paraphrased? No, right? We have the notion of some common information, or they call it celebrities, right? Biographies of celebrities like Modi or Trump will appear multiple times, whereas biographies will have tail biographies as well, right? And so that's what they want to study next, that in this control setup, they pre-train on 100K minorities. What they are calling by minority essentially means that there is only there are no paraphrases. We have only one biography per person, and that also in that also sentences are randomly permuted. This was the worst case, if you remember, that we saw. But along with that, we add celebrity data as well, meaning the previous data that we had, 100K biographies, and there everything is permuted, and we have 5 paraphrases, right? So we have with data augmentation, and then we fine tune using, there are 2 ways of fine tuning. We can fine tune with the minority data, question answers on 50K minority, right? Notice that for both celebrity and minority, there is in-domain and out-of-domain distribution. We are always training on in-domain and testing on out-of-domain, right? So we can train on minority QAs or on celebrity QAs, and then test on 50K minority QAs. So the result here is that it helps, right? So let's not go into the details here. You see that it's 86% performance. Even if you paraphrase data, even if you have data augmentation for some celebrities, right? that will also help the model to learn the art of extracting that information, right? All right. So yeah, so this is the final result that they present, right, in the first paper. The first result was that mixed training, right, where we have biographies as well as QAs in the same phase. It helps, but it is very unrealistic because it requires 80% QA data, which is, it's not there in the real world. Then they looked at pipeline process, which is typically followed. We pre-train and then fine-tune. This does not work without knowledge augmentation, and we need to do knowledge augmentation. And the good news is that we can do it only on the celebrities to extract the knowledge. We have not looked at one result, which is about the bidirectional model. So they claim that bidirectional models, even with mixed training or with knowledge augmentation, they are not able to learn these tasks on out of domain. So we'll not go into the details here, but this summarizes the first paper in the series, and these are the results that we just looked at. Let me just motivate the second paper here, what they are actually looking in the second paper, and then we'll finish the lecture. So recall that again I'm coming back to the same counter example, which is was Sachin born in an even year? The question was answered incorrectly, and the first reason that we wanted to rule out was that whether model can actually extract the birth date or not before it even reasons on it, right? So we ensured now that model can extract. Let's ensure that this is true. Now if it fails, why it fails, that's what we want to understand, right? Let's also assume that this is also gone. The model knows what even means. We will ensure that model knows what even means, right? Is it because, if it is answering it incorrectly, is it because model is not able to manipulate the extracted data? And that's what they call data manipulation, right? Is it that the model can extract the birth year, knows what is even, and still cannot answer, right? And if it answers correctly, is it because of cheating? By cheating here, what I mean is that exactly the same sentence it saw in the training data, right? So for example, if we ask this question to ChatGPT, it will update its parameters to answer it correctly the next time, right? So we want to rule out this part as well, and we want to rule out this part as well. We want to design control experiments to study E and A, right? We want to study when can model in its true sense extract the information and then reason on top of it, right? So that's what they call knowledge manipulation, and they design experiments to study three kinds of knowledge manipulations. One is classification. So this is a classification task, right? You have to first extract birth year and then classify it into, you have birth year and then classify it into even and odd, right? So this is a classification task. The other is comparison, comparing the birth date of Sehwag and Sachin, for example. The next thing that they try to study is inverse search, which is that you give me the attributes and you have to guess the name of the person, right? Who was born on this date and graduated from MIT and works at Meta, for example, right? This is inverse search. And then the last part is partial or dual retrieval, which means that for example, birth date has three attributes: month, date, and year, right? Is it that the model is able to extract the entire birth date but not the year, right? So this is what they call partial retrieval. And dual retrieval is that can it extract the birth date as well as birthplace, for example, right? So these are their findings. Interestingly, they observe that models can actually extract the birth date but not the year, right? So this is very interesting. And the other observation is that they can do classification, right, but only if they follow chain of thought. So what it has to do is that it has to first, if I'm asking it for classifying into even and odd, right, recall that we saw in the example as well, it first said no and then extracted that information and then corrected itself, right? So if it sees that in its context, if it's extract, then it can reason over that knowledge. And right, so it has to first extract, and only then it can reason. That's what they figure out. So without chain of thought, classification doesn't work, and knowledge inverse search is impossible. No matter what you do, the models will not be able to do inverse search unless you put that specific question in the training data, or you have that inverse information in the training data, right? And now, so this is very interesting that these models are not even able to answer such small questions like classification into even and odd, classification year into even and odd, even if it knows the year, right? So we can use such things to devise maybe Turing tests to distinguish between AIs and humans, and that's what they propose in this second part, 3.2. Right, so I think with this we will end the lecture, and in the next lecture I think Tanmay will continue from here. Either we'll see whether we want to dive deeper into the knowledge aspect of it only, or we want to look at the other building blocks, which is reasoning or structure, language structure. Right. Okay, thank you.